I guess it depends on, I mean, if we're in, so we could say something like, that's like T1, so sum over, I have to choose my words carefully here. It depends on how much time we have left. 20 minutes? Oh, okay, I've got no excuses then, curses. 15 minutes, all right. I mean, this should be equal to, if you look at this, what do we have? We have something it's linear, right? And each one of these, how to say this? Uno momento. So the question, what I'm struggling with is how to motivate telling you that this is the determinant. I mean, this is, of course, the determinant of t. This, for all intents and purposes, can be taken as the definition of determinant. So this has to be a scalar multiple, right? So lambda n goes from n forms on V to n vectors on V to n vectors on V, right? But there's only one n vector on V up to scalar multiplication. It's just E1, wedge E2, wedge dot wedge En. So it has to be some number times this again. That's inescapable, right? And my claim is that that number is what we call the determinant. Now I can work this out, yeah?
Is that the determinant of the standard matrix of the transformation? Or
yes. So the determinant of the standard matrix of transformation will be the determinant of, we define the determinant of a linear transformation to be the determinant of that linear transformation with respect to any basis. Any two bases are related by a similarity transformation, so it would be like P inverse AP. And so when you take the determinant of P inverse AP, you get back to determinant of A. So the choice of basis is immaterial. But you know what? Just to make this more concrete, I'll take your let's look at V equals to Rn for just a second here, right? Then if I have T E1 wedge T E2 wedge wedge T En, what is that? Well, that's exactly column 1 of T wedge column 2 of T wedge wedge column N of T, right? And so I could rewrite that as a sum over I1, I2, In of, well, what I would have would be T, let's see here, to get column 1, I do T I1, 1. That's column 1. And then column 2 would give me Ti 2, 2. The 2 is for the column 2. And so forth, Tin for the nth column. And then, of course, I've pulled these out using the multilinearity of the wedge product. And what I'd be left with, of course, is the T. Oh, man. You see what I've done? Can we have our cake and eat it too? Is it okay if I leave the indices both down? Technically speaking, if I follow my conventions I was trying to impose upon us last time, I would be writing this. Yes? If you'll forgive me for not doing that for a moment. This is the wedge product. Now, how can I rewrite this in terms of just E1 through En? In other words, I want to permute these. I mean, this has to be 1 through N here, or it's 0, so who cares? But, I mean, it is 1 through, I mean, well, this doesn't have to be 1 through N. This could have like a repeat or something. The point is that this is exactly epsilon I1, I2, In. Now here I'm talking about the purely combinatorial epsilon 1 through n. I think some people would put a 1, 2, data n upstairs to indicate this has no dependence on the metric, but that for another day. Anyway, this is E1, E2, wedge, wedge En. And of course, if you look at this paired with that, right, that is exactly what I defined the determinant to be earlier this semester, right? The determinant is the sum over the Levi-Civita symbol paired with column, like the, column 1, column 2, column 3. So it's the completely anti-symmetrized multilinear sum over the columns of the matrix. That's the determinant, and that's exactly what's consistent with this. So there's the connection between my earlier, one more step, fine. And of course, if I was on an abstract vector space, I'd have to think about these being the abstract abstract matrix with respect to the basis, but it's the same calculation. Now that's not what's interesting. That's just the definition of determinant as experienced in wedge products, although it is interesting because once you have this definition, you can immediately see why the determinant's 0 if two columns are linearly dependent. Or if they're equal. If two columns are equal, then you can permute the wedges and you got wedge of the same vector with itself, which is 0. So that's why any column repeated in the determinant is 0. It also gives you the fact that you got that multilinearity. It's just manifest in this definition, the multilinearity of the determinant. It's just there. But that's also true of my definition. But here's the true power. You guys are going to prove this. It's not going to be hard to prove these. These are easy, pretty sure. I'm sure about this. I'm slightly apprehensive about this one. I'll let you know once I try it how bad that is. I hope it's not too bad. So, what's the biggest, baddest identity about determinants? Right. So let's try that. So let's look at the nth form of A composed with the nth form of B acting on E1 through En, right? This, oh man, just a second. No, it's fine. Sorry, I've been reading a couple of different books. Sometimes I forget which book I'm thinking of. It's fine. This one's fine. So, so you have that this is equal to, if we believe your homework problem, this is equal to what? Right? So this, by definition of determinant, will be what? The determinant of the product, right? Because the composite of two linear transform. I'm using A for the transformation and the matrix. I'm sorry, maybe I should do like. Would you like me to make a distinction between transformations and matrices that doesn't matter? So, okay. So determinant, yeah, okay. Determinant AB, right? On the other hand, this, right, is equal to lambda NA of this, right? Which is what?
You're saying that A can be a transformation.
I am abusing notation. I am saying A and B are both matrices and transformations. If you would like if you'd like, here we go. T, let me fix it. T, I know it's going to be a bother. So let's let this be T and S. This is T composed with S, right? So here we have determinant of the matrix of T composed with S, let's say, and over here we have the matrix of S. But this is a linear transformation. This is a number. So we can pull it out. And then we have determinant of S, lambda n T, of E1 which is, so this, of course, is just determinant of S, determinant of T, E1 wedge, wedge En, but that's equal to, on the other side, determinant of T composed with S, E1 wedge En. So you get that this and that are equal. But of course, we also have the theorem that this is the matrix of T matrix multiplied by the matrix of S. That's true for standard matrices, but it's also true for the representation of the standard. It's also true with respect to an abstract basis. The matrix of the composite is the product of the matrices of the linear transformations being composed. That's true, both in the standard matrix case and in this case. And so we get the determinant of A times the determinant of B is equal to the determinant of AB for all AB. Now that seemed easy. The devil must be in the details. Where is the devil? I know where the devil is. The devil is in proving the properties we didn't prove. It is fleshing out the combinatorics of the alternating symbol. That is where the difficulty has been shifted to. Because I have worked this problem before from this technology, and it is an intrinsically difficult problem, even with this really nice notation to show that this is equal to that. It is hard to directly prove that. So this being so easy, that it must be that, and that's a really, really a selling point for the wedge product is that it has naturally encoded that combinatorics of the determinants in terms of just the natural properties of the wedge, which is just that the wedge product is associative. And to wedge two p vector and a q vector together, basically what you do is you just erase the wedge in between, and that's it. When you look at the wedge product in terms of how it relates to the tensor product, that's technical. But if you just look at wedges, if everything's just wedges, you just behave normally. It's very, very easy, like we did here, right? Oh, so one of the interesting things to ask about this is, what is the matrix? What does the matrix of this thing look like? So the matrix of the pth exterior power of T with respect to the usual, let's say, EI, such that I is an element of the increasing indices, increasing indices of length P over N, then the matrix, if you write this as something like a sum over, how's it go? The notation here. Sum over J of EJ, sum over J of like T Ji like that, EJ, then this matrix is pretty interesting. It becomes the determinant when you look at the nth, when you look at p equals to n, but before that it's like matrices of minors. So one of your homework problems, I have you explore this in the case, I think, over a 3-dimensional space. You look at, I ask you to find the one for 2, all right? I asked you to actually calculate this matrix in the case P equals 2 and N equals 3. Now, that would be much meaner if it wasn't the fact that I'm going to provide you a copy of Rentlen. Hopefully Thursday I'll have it for you. And the answer is actually exercise 2.9. So just, I don't want you to work in the dark. But it's very interesting. And if you look at what this does, it gives you a way of understanding all these kinds of weird properties of determinants you saw before in terms of how they're just flowing from the natural exterior algebra. It's a very nice way of thinking. I can't emphasize it enough. Now, everything we did with vectors, we could equally well have done with forms here, right? We could talk about P forms and Q forms and so forth. But anyway, so next class, I might do Hodge duality. I think I might put that off. Hodge duality, when most interesting, has a coordinate dependence. So probably next time I should talk about manifolds and tangent spaces and such, and then we'll go from there. So thanks.